And so in this section, we're going to be looking at this idea of what makes the periodic table the greatest cheat sheet literally on our planet, right? And so one of the things that we want to spend some time understanding in this unit is, why is the periodic table organized the way it's organized? Why does it look the way it looks? And most importantly, what information does it tell us so that we don't have to memorize as much stuff? What a concept. I'm all for doing less work. So if we have this great resource available to us that takes and gives us all this information, then let's make sure we can look at it and we can understand it to the best of our abilities. And so we already saw from the previous unit that the periodic table is not randomly organized to look how it looks. In other words, it's not like someone just had one too many drinks and decided, you know what this thing needs? We need to have random columns in different locations. So I want these guys over here, and then I want to make sure that I have these guys that seem to be lost over here, right? And don't forget about our lost boys down here at the bottom, these guys over here. So what we saw in the previous unit was that each of those blocks represented a different area which corresponded to a sublevel or a very specific shape of an electron cloud. And so we said last time that over here, this was our S block, right? These guys over here were our P block, the transitional metals are better known as the D, and down here our lost boys are of course going to be our F block, right? And so the idea is that we already can see that there seems to be some logic to this periodic table, but this was not always the case. In fact, the first person that tried to give us some type of structure to our periodic table was a gentleman by the name of Mendeleev, right? And so Mendeleev actually organizes the chart by similar properties rather than by mass of elements. Understand that prior to Mendeleev, what scientists were doing was that they could determine the mass of an element, and so they rationally thought, well, the lighter elements are first, the heavier elements are later. But when they tried to start to find some rhyme or reason as to where elements were located, that really started to fall apart. So instead, what Mendeleev does, and we'll kind of zoom in so we can see this, is he looks at elements that have similar characteristics. And a good example would be something like the halides, so fluorine, chlorine, and bromine. And what he notices is that these elements are really good at, for example, they're good at stealing electrons. They tend to form the same type of compounds with certain elements. So if you react them a certain way, it doesn't matter if it's fluorine, chlorine, or bromine, they all seem to interact in a similar fashion, right? They seem to have certain properties that are predictable. So yes, their melting points are increasing, but they increase in a very predictable fashion, right? They always form diatomic molecules. And so what Mendeleev comes up with is he says, you know, if I were to do this in an old-fashioned way by mass, when I go to group these elements, I may end up saying something like, by mass, chlorine, sake of argument, should be, let's say, over here. And that's fine if you do it by mass, but the problem is that then if you try to compare, let's say, oxygen to chlorine, they don't behave similarly. Chemically, they're very different from one another. They don't seem to have anything, quote unquote, in common. And so this is why Mendeleev says, let's for a moment forget all about these masses and instead focus on properties. And so, for example, he takes elements like the alkali metals, right? So he takes the alkali metals and he notices that things like lithium and sodium and potassium all behave very similarly. These are highly reactive metals. These are metals that immediately give up an electron. And so what he does is he starts to group all of these different elements by these properties. And the more properties you share, he theorizes, then these things need to belong together. Now, this becomes very critical because at some point, and this is again 1800s when he's doing his work, what Mendeleev is aware of is that we have yet to discover two elements, gallium and germanium. And so what Mendeleev does when he's creating his chart, when he's creating his table, is that he actually leaves a blank for these elements that, according to him, quote unquote, haven't been discovered. Because you see, we knew about carbon, we knew about tin, we knew about lead, but he goes, there's a really big gap from the time we go, let's say, from silicon to tin. We're missing some information. And so because of that, what he's able to do is that he's actually able to leave a placeholder, and he takes it a step further, and he actually even says things like, you know, when we find this element, whatever it is, right, I bet that its properties are going to be, and he started to describe the properties, including its melting point, how it would behave chemically, etc., etc. And lo and behold, scientists now had kind of a blueprint to follow. And so within a few short years after he publishes his periodic table, scientists, sure enough, find germanium, and eventually they find gallium, right? And it falls very much within the parameters that Mendeleev predicted. So, because of this, Mendeleev is often referred to as the grandpappy of the periodic table. He is the first person that really looks at the table from a very large holistic perspective, and he says all of these things have to work together in some fashion. There's got to be some relationships between all of these elements. And so by doing this, what he's able to do is he's able to start clumping elements together by their properties, both physical and chemical, and as a result, he's able to say a lot of intelligent things regarding our periodic table. Now, what's the biggest knock on Mendeleev's table? Well, as we said, he doesn't understand why a lighter element may be after a heavier element. In other words, why the mass of something that is lighter, which in theory should come before, ends up being placed afterwards because the properties align more with a group of elements. So again, a good example of this would be something like, if you look down here, I don't know if this table has it to that level. It doesn't. It just has the general mass. But here's a good example. So if we look here, what we'll find is that we have cobalt with a mass number of roughly about 59. Right? So here's my cobalt coming in at 59. And then nickel is coming in at about 59 as well. So why put nickel after cobalt if they both have a similar quote-unquote mass number? And according to Mendeleev, what he would have told you is, he goes, well, I don't know exactly why, but I know that nickel, palladium, and platinum all share similar properties. More so than, let's say, rhodium and iridium. So this is how Mendeleev scales his chart. It is not until we get into about the 1900s, so until we have the advent and the understanding of electrons and subatomic particles, that you have a gentleman by the name of Mosely. And what Mosely does is that he actually organizes the table by increasing atomic number. In other words, Mosely is able to say that the chemical properties or chemical characteristics of an element are dependent upon the number of protons in its nucleus, right? But Mendeleev could not have said that because Mendeleev did not know about protons or neutrons or electrons or the nucleus or anything of that nature. So by the time, like I said, early 1900s, Mosely comes along and he explains Mendeleev's observations, and he goes, this is why the lighter element might be after the heavier one, because when we look at the atomic number, we now organize our periodic table by increasing atomic number, which means then that as we go across, aluminum has 13 protons, silicon will have 14, phosphorus 15, etc., etc., etc. Now, why is this idea of atomic number so important? Well, because what Mosely kind of discovered unknowingly, like what his discovery led to, was that when we look at trends on the periodic table or patterns that repeat, are you ready for this? Periodically, what a concept. But when we look at these trends or patterns that repeat periodically, what we find is that what is really driving these trends is the ability of the nucleus to attract electrons, okay? And so if we kind of stop and think about it, let's go back to what we learned in the previous unit of how exactly is my atom set up. So remember, the electrons were in these electron clouds, and the whole point why we had those different shapes to the electron cloud was so that every so often an electron could swing by the nucleus, experience the attraction of the nucleus, and stay attached to that nucleus, therefore staying attached to the atom, right? So what Mosely is saying then is that if we're going to be very concerned with protons, because that determines our chemical characteristic, what we now understand is that the atomic number, or the number of protons, is really the nuclear charge of an atom. Now let's break this down. Nuclear charge, for lack of a better word, represents the amount of positiveness, very technical term, right? But the amount of positiveness, the amount of positive charge that the nucleus has, right? Now, it would make sense to me that the more protons are in that nucleus, the greater the nuclear charge is. And that is true. But here's where it gets tricky. If a nucleus is getting more and more positive, then in theory, the more protons you have in the nucleus, the smaller atoms should get, because those protons should hug and pull all the electrons closer and closer and closer in. And what we find is the exact opposite. As we go down the periodic table, so for example, if I compare something like aluminum to gallium to indium, right, what I'm going to find is that as I go down, the atoms are getting bigger. They're increasing in size, right? Likewise, we see that other patterns and other trends seem to occur, and we'll speak about those in a moment, but all of those seem to occur based off of that idea. So why, if I'm adding more and more protons to an atom as we're going, down the periodic table, as we go further and further down, why are my atoms getting bigger? And in order to answer that, we have to talk not about nuclear charge, but rather effective nuclear charge. And this is the big distinction, that the effective nuclear charge, or the ZEF, Z effective, right, is going to take into account not only the nuclear charge, in other words, how many protons does the nucleus have, but it takes into account the shielding that the core electrons do. So what do we mean by that? Well, to figure this out, it's best if we have a little drawing to give us an idea of what's happening. So let's pretend for a moment that this represents my nucleus, right? So this is my nucleus. It has a certain it has a certain nuclear charge. Let's say that we were looking at something like, sake of argument, neon, and so we're going to give this guy about 10 protons, okay? Now, so let's just put over here, so this is my 10 protons. Now, here's the thing. I would expect, if it has 10 protons, that as I start to fill electrons up, so let's say the first two go here, right? Then the next electron, right, wants, quote unquote, to get closer to it. It wants to be just as close. But what we saw in the previous unit when we talked about modern atomic theory and the electron cloud model is that in this first energy level, I can only fit 2 of these electrons. And since only 2 of those electrons can fit, what happens is the minute I try to put a third one in, it gets repulsed. It gets pushed up. So now notice what happens. This electron that's way out here is no longer experiencing the full attraction of the nucleus. Why not? Because every time it gets pulled in by the nucleus, the core electrons, or the electrons that are between this outermost and the nucleus, are going to repel it. And so what happens is when we talk about effective nuclear charge, we're looking at this give and take between what the nucleus normally attracts and pulls and what the core electrons will repel. And if the core electrons are doing a better job of repelling than the nucleus is attracting, then the effective nuclear charge drops. If the nucleus can overcome whatever the repulsive forces of the core electrons are, then the effective nuclear charge goes up. And this idea of effective nuclear charge is what is going to be vital in determining the size of the atom. Because what we're going to find out is that there is one fundamental meaning of life. There's one fundamental rule and meaning to our entire universe. At the end of the day, the reason why you exist, the reason why you're here right now listening to me, the reason why all matter and our universe is what it is for a simple, easy concept. You ready? At the end of the day, size does matter! And the smaller you are, the more attractive you are. So we take it one step at a time, one tick at a talk, and you'll be there in virtually no time.